Okay. Yeah. I think we can start now. Okay. Okay. Yeah. I think we can start now. Okay. Okay. Yeah. I think we can start now. Okay. Yeah, okay. We can start now. Good afternoon and probably good morning, good evening to all of you accessing this Combinatorics today's series from various time zones. Welcome to the 7th edition of this series already. We would like to extend our gratitude to the Dean of the Faculty of Mathematics and Natural Sciences ITB, Professor Wahyu Sri Kutomo, for the constant support to this event. And of course, our big welcome to today's speakers for this event, Professor Peter Cameron, one of the world prominent combinatorists. We are very lucky to have you as our speaker today, and we are excited to listen your lecture very shortly. Professor Cameron, how are you today?
I'm fine. Ready to go?
Okay, so how's the weather in since Andrew there right now?
It's cool but fine. Nice autumn day.
Okay.
Glad to hear that.
So it's great to see you virtually, and thank you very much for your time today, and we really appreciate it. In this occasion, I also would like to welcome all colleagues, friends, and students attending this program. And we are really happy to have you here. And Professor Cameron, I would like to give you a report that the audience here are from various countries, not only from Indonesia. Some of them from Malaysia, Japan, Thailand, Philippines, and some from India and others, other countries. And I should mention that this program is organized by the Combinatorial Mathematics Research Group, Faculty of Mathematics and Natural Sciences, Institut Teknologi, Bandung. And this year, we will have 10 editions of this series. And the speakers are all outstanding combinatorists, various countries, from United Kingdom, and then from Australia, from Japan, French, Germany, India, and also Spain. And now we are very excited and honored to have Professor Peter Cameron from University of St. Andrews, United Kingdom. And he will deliver a lecture with the title Graph Defined on Groups, and will be chaired by Dr. Joko Supriyanto. Before I give the control to Dr. Joko, I would like to invite our Dean, the Dean of Faculty of Mathematics and Natural Sciences, Professor Wahyu, to give a welcoming speech. Professor Wahyu, time is yours. Professor Wahyu.
Thank you, Pak Edy. Assalamualaikum all over.
Yeah, okay.
Yes. Yes. Yeah. Can you hear me?
Yeah, right now. Yeah, okay.
Pak Edy?
Yeah.
Okay.
Yeah.
Thank you. Okay. Greetings, everyone, ladies and gentlemen, lecturers, researchers, colleagues, students, and all participants from all over the regions. Welcome to today's Combinatorics Day series number 7. And it is an honor and great opportunity to be here with all of you, attending and following a lecture which will be given by Professor Peter Cameron from the University of St. Andrews, United Kingdom. And the title of his lecture would be Graphs Defined on Group. On behalf of the Faculty of Mathematics and Natural Sciences of ITB, I would like to express my sincere gratitude and appreciation to Professor Cameron, while wishing that this lecture will instigate further discussion and knowledge sharing, and of course, elaborating the possibilities of having new collaboration among academics and researchers who are attending this webinar. I would like to also thank Professor Edy, Pak Edy, and all colleagues from the Combinatorial Mathematics Research Group, all the head of mathematics and actuarial science programs, either undergraduate and graduate levels, for keeping this webinar agenda alive. Thank you very much, Pak Edy, Pak Joko, Rinovia, Bu Nuning, Bu Novriana, and others. And please enjoy this webinar and stay safe and healthy. Once again, thank you, Professor Cameron, for giving us the lecture. Thank you very much.
Thank you, Pak Wahyu, for the speech. And now I would like to ask Dr. Joko to chair this talk. Pak Joko?
Okay, thank you.
Yeah.
Yeah, okay, thank you, Paddy. I'll try to share my slide. Okay. Okay. Hello, everybody. Although I believe that almost all of you have known Professor Peter Cameron very well, but let me first introduce him to all of you. Professor Peter Cameron was born in Toowoomba, Australia, and he studied at Oxford University for PhD under the supervision of Professor Peter Neumann. And he has also a teaching position, first at Oxford University and then at Queen Mary University of London until he retired at 2012. And his current position now is an emeritus professor at Queen Mary and a half-time professor at the University of St. Andrews, Scotland. It is the Scotland's oldest university. And his research interests, including group theory and combinatorics. And he has supervised around 40 PhD students. And he also received many awards. Among them are the Senior Whitehead Prize from the London Mathematical Society, and also the Euler Medal from the Institute for Combinatorics and its applications. And this is Professor Cameron's profile as described by the Scopus. He has published around, almost 300 scientific publications with a great number of citations. Moreover, he has also written around 7 or 8 books in mathematics, and 5 of them are, as you can see, ranging from counting to set logics and categories, and from algebra to permutation groups. This one of mathematics books, my favorite books in mathematics, permutations groups. And also, he has written many lecture notes for undergraduate and master students, and also for postgraduate students. And all of this note can be freely used by all of you by visiting his blog. Yeah. The page of that blog can be as you see in the in my slide. Yeah. Okay. As you can also see, the topics of his lecture notes is varying from algebra into probability, from cryptography to enumerative combinatorics, from classical groups into projective and polar spaces. Yeah. Okay. Now let's invite Professor Cameron to give a talk. Yeah. Professor Cameron, please. Time is yours.
Thank you very much. And thank you for that generous introduction. Let me just share my screen. There we go. Okay, so I'm going to be talking about a subject which goes back to the middle of the 20th century, but recently there has been a lot of development and there are many unsolved problems. And partly I've chosen to talk about this because I can only tell you about some of the things that have been done, but you will see from the talk that there are many unsolved problems, and I would really encourage you to try take some of them and have a go yourself. And please do let me know how you get on with it. So I'll be talking about graphs and groups, two of my favorite subjects. And I'll assume that you have at least some familiarity with graphs and groups. So the graphs will almost always be simple graphs, so no loops, no multiple edges, and occasionally the edges will be directed, but usually they'll be undirected. So just the nicest and simplest type of graphs. And so this subject is really part of algebraic graph theory. So in particular, we're studying graphs where the vertex set is some kind of algebraic structure, and the graph reflects some part of that structure. So as I say, it's a fairly new area, but rapidly growing. I'm going to be talking about groups, but people have also proved things about other kinds of algebras, semigroups and rings in this area. But I can't tell you everything. In June this year, I gave an 8-hour short course on this subject, and even in 8 hours, I was not able to cover everything. The notes and the videos from that course are available if you're interested. So if you want to know more, you can look there. If you go to my St. Andrews webpage, you'll find a link right at the top that'll take you to the material from that course. Anyway, so graphs and groups. So here's the prototype example. If I give you a finite group, well, if you take two elements x and y in the group, maybe they commute, that is maybe xy is equal to yx, or maybe not. So that's just the setup to define a graph. So we make a graph whose vertex set is the group, and we join x and y by an edge if xy is equal to yx, right? And there's a remarkable amount of information about the group that is encoded in that graph. So the graph doesn't tell us everything about the group. You can have different groups with the same commuting graph, but it carries a lot of information. So for example, what does it mean for a vertex to be joined to all the others? Well, that means it commutes with everything in the group. Well, that by definition is the center of the group. So we can recognize the center of the group from the graph. And if you take a vertex x and you look at x together with all its neighbors, they're all the elements that commute with x, and that's also a famous subgroup in group theory. That's the centralizer of x. So things like that are available to us from the graph. The graph tells us about that. So this graph, well, it didn't really appear in this paper in 1955. Brouwer and Fowler, this is maybe one of the foundational papers in the study of finite simple groups. They used the commuting graph without ever using the word graph. So they were interested in the distance between two elements of the group, and that distance was measured by steps in the commuting graph. So the graph was there underlying what they were doing, and their first result, the first theorem in the paper says that if you have a group with more than one conjugacy class of involutions, then any two involutions have distance at most 3 in the commuting graph, not using the identity. So you can take at most 3 steps to get from any element of order 2 to any other. And so basically this paper was about the centralizers of involutions, which of course then became one of the really fundamental ideas in the classification of finite simple groups. So this is where it all began, and this is where the subject I'm talking about began as well. So why might you want to study graphs on groups? Well, I think there are 2 main reasons. There's a third reason which I'll come to. First of all, you can use the graph to understand the group better, and this is exactly what Brouwer and Fowler did, because by using this graph, they were able to prove some very strong statements about centralizers of involutions in simple groups. So you use the graph to understand the group. The other thing is that you might get graphs that are interesting in their own right, or perhaps useful. These graphs might be good networks, might have good connectivity properties and things like that. Or maybe they don't. Sometimes they're just hopeless, but if you explore this, you might find some interesting graphs in this way. So I'll give you an example of that in a moment. So both of these, we've seen how this one applies. I'll give you an example of getting some, I think, rather beautiful graphs out of groups. And this is an example of a graph called the power graph of a group. So this was only defined in about the year 2000, but now there are many, many papers on it. So the rule is you take the vertices once again to be the elements of the group. You join x and y if one of them is a power of the other. So if x is equal to y to the power m, or y equals x to the power m for some number m. So that's the power graph of a group. And can I find an interesting graph from the power graph? Well, I'll show you that I can, but I might have to take the power graph and manipulate it a bit, cook it a bit to get something beautiful coming out. So this is what we do. So the group I'm going to take is the Mathieu group M11, discovered by Mathieu in the 19th century, the smallest of the sporadic finite simple groups. So its order has 7,920. So if we take the power graph, we're starting off with a graph with 7,920 vertices. That might sound like quite a lot, but there's enough symmetry in this graph that computational tools are readily available to analyze it. And all the computations I'm describing were done in the computer algebra system GAP. So first of all, what can we say about this graph? Well, the identity is joined to all the other elements because it's a finite group. So if you take any element of the group, some power of it is equal to the identity, and therefore it's joined to the identity. So the identity is joined to everybody. And that's not so interesting. So we delete the identity and we look at what's left. And in the resulting graph, what you find is that there are elements of various orders, but 5 and 11, they talk only to one another. So the elements of order 5, an element of order 5 generates a cyclic group of order 5, and the elements in that cyclic group, apart from the identity, are joined to nothing else. So that means we have a lot of little complete graphs of size 4, in fact 396 of them. And similarly for 11, so we get 144 complete graphs of size 10. And that's just kind of rubbish, so we throw it away, and we look at what's left. And what's left is 4,895 vertices, and the graph on that set is connected. But we're going to still cook it a little bit further. We do two more reductions. First of all, let's call two vertices closed twins if they have the same closed neighborhood. Now, if you take two elements of the group, let's suppose that they generate the same cyclic group so that each of them is a power of the other. Then they will have the same neighbors, because if you're a power of one of them, you're a power of the other also. And so there will be lots of things that will happen many times. These vertices have the same closed neighborhood, so they have exactly the same neighbors, and I don't need to distinguish between them. So I just shrink every closed twin class down to a single vertex. So I call this twin reduction. So I reduce all the closed twins to all the sets of closed twins to single vertices. And then that leaves me with 1,540 vertices. So we've already made the graph quite a bit smaller. And now there are, in this resulting graph, there are vertices that are open twins. They have the same open neighborhood, so we can collapse them as well. And that brings us down to 1,210 vertices. And that's as far as you can go with twin reduction. So let's just look at the graph that we've got on these 1,210 vertices. Its automorphism group is exactly the Mathieu group M11 that we started off with. Now, that's not necessarily the case, but it happens to be the case for this particular graph. And if you look at the way it acts on those vertices, they fall into four orbits with sizes 165, 165, 220, and 660. And we can look at edges of the graph going between those orbits. So if I take a 4x4 matrix whose ij entry tells me how many edges go from a vertex of OI into the orbit OJ, then the matrix will look like this. So this is what we call decomposition, or some people would say this is well, it doesn't matter. This is the matrix you get, and you can tell quite a lot from this matrix. For example, the first vertex, the vertices in O1 are joined only to vertices in O2. Vertices in O2 are joined to vertices in O1 and O4, and so on. And you can see that the graph is bipartite. All the edges go from O1 union O4 to O2 union O3. So there are no edges within O1 union O4. That's the 4 zeros around there. And these 4 zeros in here tell you that there are no edges within the set O2 union O3. So it's a bipartite graph. And if you work out its diameter, it turns out to be 20, but its girth is also 20. And to have a relatively small graph with such comparatively large girth compared to its diameter is quite interesting. Now, each vertex in O1 is joined to 1 in O2, each vertex in O2 is joined to 1 in O1. So those edges just form a matching. And if you think for a minute, you see that the really interesting part of the graph is O2 union O3. So if we look at O2 union O3, then by joining two, there are no edges within that set, but we join two vertices if they lie in different orbits but have a common neighbor in O4. That rule will give us a graph with no edges within O2 or O3, but there will be edges between O2 and O3. And that gives us a smaller bipartite graph with bipartite blocks 165 and 220, automorphism group M11. Vertices in the first part, O2, have valency 4, vertices in O3 have valency 3. The diameter and girth are both equal to 10, which again is comparatively large for a graph on just 220 vertices. And I feel this is the only one I looked at. I just chose this group more or less at random, not quite. I'll tell you how I chose it later, but I find an interesting graph. And I feel fairly confident that you could pick other interesting groups and get nice graphs out of them by this kind of method. So I think there are interesting things lurking there. So that justifies my second reason for doing this. The third reason, let me just say, is because this gives us lots and lots of graphs with interesting properties. So we can ask about their properties. Are they connected? What's their diameter? What's the clique number, chromatic number, things like that. And I'll talk about some of these questions as we go along. But first of all, let me actually tell you about the graphs that I'm going to be considering. So there are many graphs that have been defined on groups. I'm going to stick to just 5 particular graphs. I'm going to start off with a group, and I'm going to consider 5 graphs based on this group. 2 of them you've already met. So there's the directed power graph. When I defined the power graph, I said you join x to y if one of them is a power of the other, but I didn't say which way round. So there's really a direction there. There's a direction so if I put a directed arc from x to y, if y is a power of x, then that gives me a directed graph. And if I forget about the directions and just look at undirected edges, I will get back the power graph. So the power graph is just what you get when you ignore the directions. The next one is something called the enhanced power graph, where you join x to y if they're both powers of an element z. So if there's some element z, such as x is a power of z and y is a power of z, which means that in the directed power graph, there are arcs from z to x and from z to y. In that case, I will take an edge in this graph here. Now, what does that mean? So that's what it means in graph theory terms. What does it mean in group theory terms? Well, x is a power of z, y is a power of z. So x and y both lie in the group generated by z, the group consisting of all the powers of z. And that's a cyclic group. And we know from group theory that all subgroups of cyclic groups are cyclic. So the group generated by x and y is cyclic. Now, here's the commuting graph that we started off with. This is the graph where we join x and y if xy equals yx. Well, if xy equals yx, then the group generated by x and y, all the elements will commute, so that will be an abelian group. So I can formulate it like this. And if I do it like this, you will see that any edge in the enhanced power graph is also an edge in the commuting graph because cyclic groups are abelian. And by the way, any edge in the power graph is an edge in the enhanced power graph because if x and y are joined in the power graph, if y is a power of x, then I can take this z just to be x. So then there's what's called the non-generating graph, where you join x to y if they don't generate the whole group. So if the group they generate is not the whole group. And the complement of that will be the generating graph, where you join them if they do generate the whole group. And those are also interesting. There are a number of others, but that will be enough to be going on with. I think maybe my video has stopped working. Can I just see whether I can do something about that? Oh, there we go. Okay. So now these graphs, as I say, they form a hierarchy. The edge set of the power graph is contained in the edge set of the enhanced power graph. That's contained in the edge set of the commuting graph. And so each is a subset of the next. And in most cases, the edge set of the commuting graph is contained in the edge set of the non-generating graph. The only times when that doesn't happen is if G is a 2-generated abelian group, and that's a very small proportion of groups. So for most groups, the hierarchy goes up to the non-generating graph. And we complete this hierarchy with the null graph at the bottom and the complete graph at the top. And that gives us a hierarchy of graphs. So we can look at them individually, or we can consider the whole hierarchy together and prove general things about it, which is what I will do partly. Now, if you know the directed power graph, you can get both the power graph and the enhanced power graph. We saw that from the definitions. Let's just go back. If the power graph, you just forget the directions on the edges. For the enhanced power graph, you look to see whether there is a vertex that has arcs going to both of x and y. So the enhanced power graph determines the power graph, but it goes back the other way too, up to isomorphism. So if you have two groups, G1 and G2, if the following conditions are equivalent, the directed power graphs are isomorphic, the power graphs are isomorphic, the enhanced power graphs are isomorphic. All those conditions are equivalent. The only thing is we don't know precisely which of the groups, which pairs of groups have this property. So the smallest example is if you work out the, I don't know if this is the smallest, but if you take, there are two groups of order 27 where every element has order 3. One of them is an abelian group. It's just the direct product of 3 cyclic groups of order 3. And then there is a non-abelian group as well. So they have all these graphs isomorphic, but the groups are not. But we don't know a complete list of when that happens. So if you have a hierarchy like that, the first question you might ask is, when can two of those groups be equal? So we'd like to know, when does it happen that, let's say, the enhanced power graph is equal to the commuting graph, and so on. So we're going to start at the bottom and work up and answer this question. So to say that the power graph is the null graph, contains no edges, well, that'll happen if and only if G is the trivial group, because as soon as there is an element which is not the identity, it sends an edge to the identity. So that's easy. The next one is much harder. When is the enhanced power graph equal to the power graph? Well, it turns out that that means that every element of the group should have prime power order. So this immediately brings us to an interesting and difficult group theoretic question, which are the groups where every element has prime power order. So if you think about the two groups of order 6, for example, the cyclic group of order 6 has an element of order 6, which is not a prime power. But the symmetric group of degree 3, S3, or the dihedral group, all its elements apart from the identity have order 2 or 3. So it has that property. So these groups are sometimes called epo groups. That's short for elements have prime power order. So this question was first raised by Graham Hickman in 1957. In 1963, when Suzuki found his new family of finite simple groups, he was able to find all the simple epo groups. But the whole classification was not completed at that time. And it happened recently that I realized that the epo groups were precisely the ones where these two graphs were equal. So I asked Natalia Maslova if she knew about a characterization of epo groups. And she didn't, but she sat down and produced one. So we now have a list of the epo groups. So this problem is now solved. The next one is, when is the commuting graph equal to the enhanced power graph? Well, there's a similar kind of condition. This holds if and only if the group contains no subgroup, which is a product of two cyclic groups of the same prime order. And there's a classification of these groups as well, which is much older, actually. It goes back to the 1960s. If G is a non-abelian group, you can ask, when is the commuting graph equal to the non-generating graph? Well, that means that any two elements that commute generate a proper subgroup. So the group is non-abelian, but any two elements that don't commute generate the whole group. So it's a minimal non-abelian group. It's a non-abelian group, all of whose proper subgroups are abelian. And this classification is much older. It goes back to Miller and Moreno in 1904. So well over a century old. And finally, the non-generating graph is complete. That means no two elements generate the group. So it's a group which is not too generated. So again, we end up with something rather easy. So that's those are when two of these things can be equal. But now, having done that, I now like to present you with a whole basket full of open problems. Suppose you have a monotonic graph parameter, so a parameter of graphs, so that when you add in more edges, it doesn't decrease, it can only increase. Now, these graphs form a hierarchy, and therefore, as you go up the hierarchy, this parameter P is non-decreasing. So as a generalization of asking when two of the graphs in the hierarchy are equal, we can ask, when do they have the same values of this parameter P? So you could take any monotonic graph parameter and ask this question. And I think you will get an interesting collection of problems in that way. So let me just talk about a couple of them. So the power graph and the enhanced power graph have the same clique number, so the same size of the largest clique, if and only if the largest order of an element of G is a prime power, because you can show that the largest clique in the enhanced, well, a clique in the enhanced power graph, a maximal clique is a cyclic subgroup. And if you take one of maximal order, that'll give you the largest one. And you want to know when is that a clique in the power graph? Well, that'll happen if and only if the group, that cyclic group has prime power order. So I think there's no hope of characterizing the groups with this property, but at least we have a test now for when the power graph and enhanced power graph have the same clique number. And here's a slightly more subtle case. So this is a result I proved with two Indian mathematicians, Swathi and Sunitha, in Calicut on in Kerala. So if you ask about matching number, the size of the largest family of pairwise disjoint edges, when do the power graph and enhanced power graph of G have the same matching number? Well, it turns out that's true for every finite group. And this was a bit of a surprise, because we don't have a formula for the matching number of the power graph of an arbitrary group. So we don't know exactly what the matching number is, but we know it's the same for the power graph and the enhanced power graph. Well, how would you prove that? You have to, you know that the matching number in the enhanced power graph is at least as big as in the power graph. So suppose you take a matching in the enhanced power graph. If all its edges belong to the power graph, then that's fine. That's what you're trying to get. Otherwise, you take an edge which belongs to the enhanced power graph, but not the power graph, and you want to somehow shuffle things around so that gets replaced by an edge in the power graph. So you've increased the number of edges in the power graph lying in this matching. So that's how the proof goes. It's not that complicated, but as I say, it's a little bit subtle. So going back to the hierarchy, we have this hierarchy of graphs. So we know when two of them are equal. So the next question would be, take two graphs in the hierarchy and look at the set of edges that belong to the larger one, but not the smaller one. So the difference between the edge sets. That forms a graph. What can we say about those graphs? And there are some special cases which are interesting, because at the bottom of the hierarchy, we have the null graph. The next one up is the power graph. And if you take the difference, it's just the power graph. And that, as I say, has quite a large literature. And if you, at the top, we have the complete graph, and just below that, we have the non-generating graph. So the difference is the generating graph. So where two things are joined, if they do generate the whole group. And that also has quite a large literature. But the cases in between have not been very much studied. I'll tell you one result about them later on, but the only other work I know is Saul Friedman, a PhD student in St. Andrews, has looked at the difference between the non-generating graph and the commuting graph. So the graph where you join two elements, if they don't generate the group and they don't commute. And he's proved some strong results about connectedness and diameter and so forth for that graph. But you see, there's a whole large collection of problems in this area as well. Plenty of open problems. So now let's go back to the power graph for a moment, because the power graph is a perfect graph. So let me just say a little bit about perfect graphs. A graph is perfect if every induced subgraph has clique number equal to chromatic number. Now, in an arbitrary graph, the chromatic number is at least as large as the clique number, because if you have a complete graph with, say, m vertices, and you want to color the vertices, you want to find a proper coloring, all of those m vertices are going to need different colors. So you will need at least m colors to do that, right? So the chromatic number is always greater than or equal to the clique number. And if equality holds for every induced subgraph of your graph, then the graph is called perfect. And this is a class, a study of these goes back to Claude Berge, and it was only, something around 10 years ago when a conjecture of Berge was finally proved, and it's now known as the strong perfect graph theorem. This was by Chudnovsky, Robertson, Seymour, and Thomas. A graph is perfect if and only if it doesn't contain any induced odd cycle of length greater than 3. These are sometimes called odd holes, or the complement of an odd cycle of length greater than 3. These are called odd antiholes. So a graph is perfect if and only if it does not contain one of those. Well, you can see fairly easily that an odd cycle of length greater than 3 is not a perfect graph, because its clique number is only 2. There are no cliques larger than a single edge, but you need 3 colors for a proper coloring. If you alternate 2 colors around the cycle, you'll get stuck at the end. Now, Dilworth's theorem, this is the easy part of it. There are 2 parts to Dilworth's theorem. This is the easy part. The comparability graph of a partial order is perfect. That is, if you take a partially ordered set, you join 2 elements if they're comparable, if one is less than or equal to the other, you get a perfect graph. So that's a source of perfect graphs. And the hard part of Dilworth's theorem says that's also true for the complement of for the incomparability graph of a partial order. But it's the comparability graph we want here, because we're going to take the we're going back to the power graph. So the power graph, if you think about the directed power graph, remember the directed power graph has an arc from x to y if y is a power of x. Now, if we were to add loops into there, that would be a reflexive relation, but it's also a transitive relation. If y is a power of x and z is a power of y, then z is a power of x. So it's a reflexive and transitive relation. And this is something which is called a partial pre-order. So it's like a partial order, except that you might have elements that are comparable both ways round. But they'll form an equivalence class. And we can turn the partial pre-order into a partial order by just ordering the vertices in each equivalence class in any way we like. And so the power graph of any group is the comparability graph of a partial order. And therefore, it's perfect. So the power graphs are all perfect graphs. That's not true for the other types of graph I'm talking about, as I'll show you in a moment, because I want to talk about universality. So if you look at the power graph, not every finite graph is embeddable as an induced subgraph in the power graph of a finite group, because the power graph is perfect. So all its induced subgraphs are perfect. And so non-perfect graphs cannot be embedded as induced subgraphs. But that's the only restriction. If you take a perfect graph, you could ask, can I find a group such that this graph gets embedded into the power graph of that group? And the answer is yes, we can. And for the other types of graph in the hierarchy, the enhanced power graph, the commuting graph, and the non-generating graph, every finite graph can be embedded. So here's the theorem. The first part says, if you take any graph which is the comparability graph of a finite partial order, then you can find a finite group such that gamma is embeddable as an induced subgraph in the power graph. So for power graphs, you can embed the graphs you can embed are precisely comparability graphs of finite partial orders. But for the other types, you can, for the enhanced power graph, commuting graph, and non-generating graph, every finite graph can be embedded. So they're universal. This class of graphs are universal. They contain all finite graphs. For the commuting graph, this goes back to Thomas Pisanski in 1989. For the others, I think it's more recent. But there is an open problem here still, which is how big does the group have to be? To say, I give you a graph on n vertices, and I ask, how large does the group have to be so that that graph is embedded in its enhanced power graph or its commuting graph? Well, we have some bounds, but we don't have precise values. Or you could ask, I want a group that embeds every n vertex graph. And again, we have bounds, but we don't have exact values. So there are interesting things to look at there as well. Okay, so I'll just give you a little strengthening of that result. So suppose you take the complete graph, the finite complete graph, and you color the edges red, green, and blue, any way you like. This is not a proper coloring, just any way of coloring the edges red, green, and blue. Then you can embed the vertex set of this finite complete graph into a group G such that red edges belong to the enhanced power graph, green edges belong to the commuting graph, but not the enhanced power graph, and blue edges don't belong to the commuting graph. So this is I'll show you that this is a stronger form of that universality theorem. You see, if you ignore the distinction between green and blue, so you just got red edges in the enhanced power graph and the non-red edges are not in the enhanced power graph. So that says the enhanced power graph embeds every finite graph. If you ignore the distinction between red and green, the red and green edges belong to the commuting graph, the blue edges don't, so you get the universality of the commuting graph. And if you ignore the difference between red and blue, the green edges belong to the difference between the commuting graph and the enhanced power graph. The others don't. So that shows that that difference is also universal. So you get a little bit extra for free out of this three-way result. And obviously there are many variants on this that you could ask about. The one I'd most like to know about is, what if you take, instead of here, the enhanced power graph and the commuting graph, you were to take the power graph and the enhanced power graph. Now the power graph is a comparability graph of a partial order, so you can't choose your red edges completely arbitrarily. They would have to form a comparability graph. And there's also a restriction on the green edges, but I won't chase that up now. Let's go on because time is running. So I would like to talk about, if you're going to investigate questions like connectedness, you see, I remarked when I was talking about the power graph that the identity is joined to all the other vertices. So asking about whether power graphs are connected, the answer is trivial. They're always connected and they always have diameter at most 2, because whatever 2 points you take, you can go from one to the identity to the other one. You can get there in 2 steps. So you might say, well, that's cheating because you shouldn't really use the identity. It's joined to everything. So you might want to throw that away, but then you might want to throw away all the vertices that are joined to everything. So you need to know which they are first. So the first thing we have to do is answer the question, which vertices are joined to all the others in, well, let's go through the graph types in the power graph. Well, this is a little bit complicated. If G is a cyclic P group, if it's a cyclic group of prime power order, then the answer is everything. The power graph is complete in that case. If G is cyclic but not of prime power order, the things joined to everything are the identity and the generators. If you take any generator, everything in the group is a power of it, so it'll be joined to everything in the power graph. If G is a generalized quaternion group, you just get the center, oops, and otherwise you just get the identity. So the answer depends on what kind of group you're looking at. In the enhanced power graph, the vertices joined to all others form a particular subgroup. This is a not very well-known subgroup called the cyclicizer of G, and there is a description of it. So these are the elements X, such that for any Y, the group generated by X and Y is cyclic. And there is a characterization of it, which I won't dwell on. For the commuting graph, well, the vertices joined to all others form the center of G, as I said earlier on in the talk. So in each case, we have a description of the vertices joined to all others. So for questions of connectedness, we could now say, well, throw them away and see whether what you've got is connected. Well, in the non-generating graph of a two-generated group, what are the vertices joined to all others? That's a question which there's no nice answer to as yet. That set contains the Frattini subgroup, because that consists of all the elements that can be dropped from any generating set. It contains the center of the group as non-abelian, but it needn't always be a subgroup even. But I want to just tell you about a few recent results on connectedness of some of these graphs. These are very nice results, and they use some quite non-trivial group theory in their proofs, but I'm not going to go through the proofs. I just want to tell you the results because I think they're quite striking. So the first one is due to Michael Judici, Luke Morgan, and Chris Parker. The second to Saul Friedman, whom I mentioned before. Third one to Tim Burness, Robert Guralnick, and Scott Harper. Okay, so the commuting graph. So when I say reduced, I mean we're leaving out the vertices in the center, so there's no cheap way of going in two steps. Then there's no upper bound for the diameter. It can be arbitrarily large. For any D, there's a group of 2 power order whose commuting graph is connected with diameter greater than D. But if you ask for the center of the group to be trivial, then there is an upper bound. The upper bound is 10, and that's an upper bound for even if the graph isn't connected. Every connected component has diameter at most 10, and that's best possible. So that's quite surprising. And indeed, this first result, people conjectured for a while that there would be a bound because they couldn't find examples, but then this was Judici and Parker who did this part, I think. So what about the non-generating graph? Well, if you take a non-abelian finite simple group, so we're just looking at simple groups here, then, and you take the non-generating graph and throw away the vertices joined to everything, the diameter is at most 5. And we don't know whether that's actually best possible. The correct answer is either 4 or 5. There are some simple groups where the diameter is 4. There is no simple group where the diameter is bigger than 5, but we don't know whether 5 can occur. So this is Saul Friedman's result. And finally, the generating graph. This time we just throw away the identity for a reason that I'll explain. So the following conditions on that graph. So this is the generating graph with the identity left out. So the first condition says there are no isolated vertices. Every vertex has a neighbor. The second is apparently much, much stronger. Every 2 vertices have a common neighbor, so that the diameter is at most 2. So if you just assume the first, then the second also holds. So these generating graphs are really rather special and rather well connected. And there's a group theoretical condition equivalent to those, which is that if you take any proper quotient of the group, so any G over N for any non-trivial normal subgroup, then that should be cyclic. And so in particular, if G is a simple group, then it has no proper quotients apart from the identity. And so all these conditions hold. So these conditions apply for simple groups. And indeed, the second one was a quite long-standing conjecture when Burness, Guralnick, and Harper proved it. Right, well, now I want to say something about some other parameters. So here's clique number. What can you say about the clique numbers of these graphs? I think clique number is an important parameter of any graph, and certainly if you want to use the graph as a network in telecommunications, clique number is important because things close together might interfere with one another. So you need to know where the cliques are. So what's the clique number of one of our graphs? Well, some cases are straightforward. If you take the commuting graph, two vertices are joined if and only if they commute. So if you have a clique, all its elements commute. So the group they generate is an abelian group. And so every clique is contained in a subgroup, which is an abelian subgroup. So the clique number of the commuting graph is just the order of the largest abelian subgroup of the group. The clique number of the enhanced power graph is the order of the largest cyclic subgroup. The reason is rather similar to what works for the commuting graph. You need to know that if you have a set of elements and only two of them generate a cyclic group, then the whole set generates a cyclic group. So that's why those things hold. But I want to say something about the power graph because there's a nice little bit of number theory that comes in here. A clique in the power graph is contained in a clique in the enhanced power graph, so it's contained in a cyclic subgroup of G. So the clique number of G will be the largest clique number of a cyclic subgroup of G. So we just need to know about cyclic groups. And also, the power graph is perfect, so that will solve the chromatic number as well, because the chromatic number will be equal to the clique number. So we don't need to do any more work to get that. I think my video has stopped again, so let's try and get that going. It doesn't seem to want to work, so maybe I'll just have to do without it. Oh, wait a bit, I see there's a comment. In the chat. Oh, yes. So, yes, please, I'm happy for you to interrupt me, but if you want to put a question in the chat, that's also fine. So anyway, clique number of a cyclic group, a power graph of a cyclic group. The value was actually worked out by three Iranian mathematicians, Alireza, Ahmad, and Abbas. They gave a formula for it. The formula took up about 3 lines on the page. Here's a simplified version, but we can learn from it something that they didn't. So simple formulae are sometimes better. So this f of n, clique number of the power graph of a cyclic group. So it just depends upon n. So if you like, it's a kind of number theoretic function. Well, f of 1 is equal to 1. And if n is bigger than 1, then f of n is equal to phi of n, Euler's function, plus f of n over p, where p is the smallest prime divisor of n. So that's a recurrence relation, which easily allows you to calculate f of n for any n. And the inductive step, what you do is you basically say, well, the phi of n generators are joined to everything, so they've got to be in a maximal clique. And the remaining vertices should lie in a proper subgroup, and choosing the largest proper subgroup will give you the largest value. And from that theorem, so from this recurrence relation here, phi of n plus f of n over p, we see it's really quite easy to show that f of n, to get the order of magnitude, it lies between n, phi of n, and 3 times phi of n. And in fact, this is true. If you take f of n over phi of n, that's bounded, so it has a limb sup, and the limb sup is this strange constant, which I've not seen anywhere else before, 2.64810, and so on and so on. So some strange constant, and here's the analytic formula for it. You take the product of 1 over pi minus 1, where this ranges over the first k primes in order, and you sum that over k, starting at k equals 0. So for k equals 0, that's the empty product, so it's 1. For k equals 1, the only prime is 2, so we have another 1, and that makes 2. For k equals 2, we have the primes 2 and 3, so this is 1 times a half, 0.5, so we're up to 2.5. So you can see this series is very rapidly converging, and you can easily work it out to as many places of decimals as you want. But of course, if you're a number theorist, you'd like to know, well, is it rational, algebraic, transcendental? We have no idea. Well, I say I do not know whether the set has other limit points. It does have other limit points, but I don't know what all the limit points are. So finding the limit points of that is another interesting question. And using that, we can find the clique number of the power graph of any group. We just look at all the cyclic subgroups. But you can't just take the largest cyclic subgroup. So here's a little example to show that. The group, that should say PGL 211, I'm sorry, has elements of orders. The largest orders of cyclic subgroups are 10, 11, and 12. F of 11 is 11, but F of 10 and F of 12 are both 9. So the clique number of the power graph is 11. Now, I'm running out of time a bit. I'd like to say I've only got a few more slides to go. So since we started a little late, if you don't mind, I'll just carry on a little longer. So I told you about EPO groups before. These are groups where every element has prime power order, and they turned out to be precisely the groups where the power graph was equal to the enhanced power graph. Now, this problem aims to extend that classification. We have a classification of those groups, but here's something, well, it's a bit different. So I'm going to define a cograph. There are various names for these. It's a class of graphs which has been rediscovered many times. It's a graph containing no induced subgraph, which is a 4-vertex path. It doesn't contain a path of length 4 as an induced subgraph. So it's the smallest class of graphs containing the 1-vertex graph closed under disjoint union and complementation. And that means you can build any cograph by starting with 1-vertex graphs, taking disjoint unions, taking complements, and carrying that on until you get the graph you're looking for. And in the other direction, if you're given a cograph, either it's disconnected and you can look at the components, or its complement is disconnected and you can look at the components of the complement. So this is a class of graphs with extremely good algorithmic properties. And remember I talked about twin reduction earlier on. You take two vertices if they have the same open neighborhood or the same closed neighborhood, and you just identify them if that happens. Now, you can do that to any graph. You can apply twin reduction to any graph, and you can go on reducing until no further reduction is possible. And the graph that you come up with will be independent of how you did the reduction. Any order of doing the twin reduction will give you the same graph. And I'm going to, just for a name, I'm going to call that the co-kernel of the graph, the original graph, because it's connected to cographs in a way that, a surprising way that I'll show you. A graph is a cograph if and only if its co-kernel is the 1-vertex graph. So in other words, if you have a graph, you do twin reduction and you reduce all the way down to a single vertex. That's equivalent to the graph that you start off with being a cograph. So that's another test for a cograph. And so interesting graphs may arise. So I took the group M11 earlier on to give you some interesting graphs. I took M11 because its power graph is not a cograph. But one of the reasons we'd like to know for which groups the power graph is a cograph is because if it's not, we're more likely to get interesting graphs as power graphs. So the question is, when is the power graph a cograph? And that includes the EPO groups, because for any EPO group, the power graph is a cograph. And with two more Indian mathematicians, Pallavi Mama and Ranjit Mehetari from Rourkela, I've been attempting to classify the finite groups whose power graph is a cograph. We haven't finished yet. We know the answer for nilpotent groups. They must be either of prime power order or cyclic of order, the product of two distinct primes. And we know the non-abelian simple groups whose power graph is a cograph, PSL2Q or Suzuki group for certain prime powers Q, not all Q, or this one other group, PSL3-4. And deciding exactly which Q this works is an extremely difficult number theoretic problem. It's related to Catalan's problem. Catalan's problem was about prime powers differing by 1. Well, something similar happens here, and but we don't know how to solve that. But I think I won't go further on to that. I'll finish up here. So a lot of my interest in this was revived by these two people, Vijay and Aparna Lakshmanan, in Kochi in Kerala in India. They ran a research discussion group on graphs and groups, and many of these things were discussed there, and some of the results proved. I'm also grateful to you for all coming along to my talk, to Professor Baskoro for the invitation. And if you want to know more, well, there's a paper here in the International Journal of Group Theory, not actually published yet, but you can get hold of the article. It's open access, freely available, and take a look. It's quite a long article, and I know more now than I did when I wrote that article, but there are many open problems in that article. So if you're interested in this area, that's somewhere where you can find more details. And so I'd just like to thank you for your attention. So thank you very much. And I'm afraid I can't get my video. There's some problem I'm having with my video. It's not working, but I will stop screen sharing.
Okay. Okay. Thank you, Professor Cameron. Very nice and inspiring talk. And before I open the time for comments or questions, as before, Pak Edy, is there something to share to all of us?
Okay. Okay. So we will give a song for our thanks to Professor Cameron. Let me see. Okay.
The colors of the rainbow so
That was beautiful. Now, I see there are some quite a few things in the chat. Shall I start off by going through that?
Yes, sure. Sure. So, please, Professor Cameron.
So there's a question here that says, 2 questions. Has any work been done in finding the metric dimensions of these graphs? As far as I know, there has not been. If there is, I'm not aware of it. So you can regard that as pretty much an open question. And the next one is, in which paper can you find the result on the characterization of cographs? If you look in that paper I gave you right at the end in the International Journal of Group Theory, it's in there. And is it possible to send the slides via email? Yes, if you just email me, I can send you the slides. Is the commuting graph always connected? The commuting graph is always connected if you include all the group elements, because everything is joined to the identity. And indeed, everything is joined to all the vertices in the center. But if you remove the vertices in the center of the group, so there's no longer any vertex joined to all the others, then the answer is maybe yes, maybe no. Sometimes it is, sometimes it isn't. Where is the position of non-commuting graph in the hierarchy? Well, the non-commuting graph is the complement of the commuting graph. And so I talked about a hierarchy where the graphs go up. If you take the complements, you get a hierarchy in the other direction, of course. So the non-commuting graph will contain the non-generating, the generating graph, but it will be contained in the complement of the enhanced power graph, or the complement, and then that's in the complement of the power graph. So they go in the other direction. And there are some results. It's actually not too difficult to prove that the non-commuting graph is always connected and has diameter 2, apart from isolated vertices. The isolated vertices are the vertices in the center of the group. Apart from those, everything lies at distance at most 2. So energy of graph. Well, there has been a little bit of work on this, for the power graph at least. I don't know whether it's been studied for the other types. I myself have not thought about that at all, but I know there have been some results about energy and about more general things about the spectra of these graphs, the ordinary spectra and the Laplacian spectra. So there are some results there. There's a survey on power graphs, just power graphs, not the other types, in the AKCE International Journal of Graph Theory and Combinatorics, I think it's called. So again, I can send you links and references to all of these things if you ask. So here's someone, here's an email address. So are there more questions?
Okay, thank you, Peter. Are there any other questions? Please, you can turn on your Zoom first, and then you can ask directly to Professor Cameron. Yes, this is from Intan.
Yes.
There's also another question in the chat, Peter.
Yes.
Chat room, yeah.
Aha. Oh, great. That's something that I never thought about. I think that's a very interesting idea. Yes. I think that's, yes, because, I mean, that's a symmetric relation, so defines a graph. Does that graph have, what properties does that graph have? I have no idea. I think that's a completely open question, and I would encourage you to think about it. Of course, it's not clear how that graph is connected to some of the other graphs I've been talking about. Are there any links? It's not the same as the commuting graph, obviously. But, well, Okay. Thank you for the question.
Any other question, please? Okay, Peter, maybe it is just a trivial question from an outsider like me. As we have known that we may obtain some classical association schemes from the action of certain finite groups on the finite sets. And from that classical association schemes, we can obtain the classical, the graph.
Yes.
My question is, are there any connection between the graph in the classical association schemes and the graph derived from the group as you explained in this lecture? Can you say something about that connection?
Yes, well, I don't know what connections there are, because you see, in almost all of those cases, you have a group acting on a set, and the action on the set is usually transitive. And you need, that's all you need to get a fairly general notion of an association scheme where you don't require it to be symmetric or commutative. But in all of these cases, you see, all the graphs I presented to you, they're built on a group G, and they have the property that the automorphism group of G acts on the graph. They're all defined in such a way that the adjacency relation is preserved by automorphisms of the group. So we have the automorphism group of the group acting on the group itself. And so we don't get an association scheme, but we do get a coherent configuration from that action of the automorphism group. And this is something that has hardly been looked at all. There is almost certainly interesting stuff to find there. Sometimes you'll be able to recognize the orbits of the automorphism group from the graph, but other times probably you won't be able to do that. And it might be interesting to find the groups for which you get an interesting coherent configuration in that way that is somehow linked to the automorphism group of the group, but also to the combinatorial properties of the graph.
Okay.
So yes, a nice question. I don't think I can give you much more of an answer than that, but worth thinking of, I guess.
Okay, okay. Thank you, Peter. There is also one other question in the chat room.
Yes, I see. Is there a relationship between commuting graph and commutativity degree? Yes, of course, there's a very close relationship. You take the commuting graph. Now let's turn it into a directed graph by putting edges in both directions and put loops at every vertex. Then the commutativity degree is the number of edges of that graph divided by the order of the group squared. Because we're just counting the pairs of elements that commute, basically. So yes, there are quite a number of results on commutativity degree, which they're all talking about the number of edges of the commuting graph. Now, I would say that the commuting graph is probably nice, contains more information. The commutativity degree is just a number, but it basically tells you how many edges the graph has, but the graph itself is packed with information. And I think you may get more by, you might even learn something about the commutativity degree by looking at the commuting graph. So does that answer the question? There's another question here.
Yeah.
Have I considered the co-prime graph of a group? I'm sorry, could you just explain what you mean by the co-prime graph? I know what the prime
Francis Campana, do you want to ask your question directly? If you want, please just turn on your camera first, and then you can ask directly to the Professor Camera. Francis, are you still here? Francis Campana?
Well, let me say something in the meantime while he
is there.
Gets ready. I know what the prime graph of a group is, sometimes called the Grunberg-Kagel graph. You take the the vertices are the prime numbers that divide the order of the group, and you join P to Q if the group contains an element of order PQ. And this tiny little graph has a surprising amount of information about the group in it. And there's a great deal of work goes into the study of this. It goes back to Grunberg and Kegel in the 1960s. They were looking at integral representations of groups and whether the augmentation ideal of the group ring is decomposable. But here's one fact. If you have two groups that have isomorphic power graphs or enhanced power graphs or commuting graphs, then their Grunberg-Kegel graphs, their prime graphs, are also isomorphic. So there is a very close connection between that graph and the graphs that I've been considering, yes. But are you there?
I think I can help give the definition for the coprime graph. So two vertex are adjacent if their order are coprime.
If the order of coprime. Okay. Yeah. It doesn't exactly fit into the hierarchy, but it is related. There's another piece of work that I've done that I haven't talked about. If you take any of the graphs in the, so if you want some more graphs to study, if I haven't given you enough graphs to study, here are some more. Take any of the graphs that I've told you about and take any natural equivalence relation on the group, such as conjugacy or having the same order. Then you take a graph where you join two vertices x and y. If something in the equivalence class of x is joined to something in the equivalence class of y in whatever graph you were considering, the commuting graph or the power graph or whatever. So these are kind of super commuting graphs or super power graphs. And the graph that you're talking about, if you take its complement, then that is related to the super power graph. It's not quite the same, but there are connections, which I can't tell you anything really striking off the top of my head about that, but I'm sure there are connections between this graph you're considering. So we're preparing a paper about these supergraphs at the moment. It's still really work in progress, but I can send you some notes about that if you're interested in. Just drop me an email and I'll send them to you.
Okay. Okay, thank you, Peter.
Can I have a final question, Pak Joko?
Yes, this is just a final question. Please, Pak Edy.
Okay, thank you. So I just wonder, Peter, is it
Yes.
is there any relation between the graph on group, because graph on group has a lot nice property, relation with Ramsey minimal graph for certain Ramsey minimal graph?
That's a good question. I don't know. I really don't know. I mean, there are certainly some extremal graphs in Ramsey theory that are associated with interesting groups, but I don't know if there's any more general connection. My feeling would be, though, that you know, Ramsey theory is hard, and the sort of graphs that tend to come up, you just, you know, they don't necessarily have anything to do with symmetry or groups. So probably there aren't very strong connections. And but that's just a guess. I don't know. I don't really know anything about that.
Thank you. Thank you.
Okay.
Okay, I think the time is almost finished. So before we go back to Pak Edy, let's thanks again to Professor Peter Cameron for the nice and very inspiring talk. Yeah.
Okay.
Okay, Pak Edy, please.
Okay. So thanks again to Professor Peter Cameron for wonderful and inspiring lecture today. And we would like to present you a certificate as a our thankful to Professor Cameron, and also portrait, what is it? Sketch of your photo. So I will show you the certificate of this event and also the portrait of your photo. Just let me see here. Okay, so this is the certificate of this event. So again, thank you, Professor Peter Cameron, for wonderful talk for today's. And also this is
Oh, right. Well, thank you. Thank you. That's very nice.
I will send this
Yes.
to you by email.
Please
And
do.
also, of course, we like to invite you to come to Bandung sometime. Yeah, when you come to Australia, just let me know. Then you can have a combined trip to go to Australia and also to Bandung, Indonesia.
Thank you. Yes, that's a very attractive invitation. Thank you. When things return to normal, I will take you up on that.
Yes. Okay. So thank you. So this is the end of our series today. And thanks to everybody here for attending this series. And we will have another lecture for 2 weeks later. So we also like to invite you all to come to join our lectures. Yeah. Okay. So bye-bye. And thank you very much. Yeah.
Thank you. Goodbye.
Terima kasih. Yeah. Bye-bye, Professor Cameron.
Bye.
Thank you very much. Terima kasih semuanya, Bapak Ibu, yang telah menyempatkan hadir pada kuliah hari ini. Okay.
Thank you, Jay. I forgot to invite you, to ask you to